Thanks a lot. So first of all, let me thank the organizers for inviting me and giving me the opportunity to share our work in this fantastic webinar series. So today I will be talking about the thermo-optical effects and how can we use them both at the level of the individual nanoantennas, as well as going towards applications in larger array and therefore metasurfaces. And so really the essential element, maybe just to give a little bit of a perspective of the activities and where we are coming from in our group, is really around how can we use photonic metasurfaces primarily for energy conversion devices. And therefore we try to understand really at the level of the individual nanoantennas, how can we control the conversion of the energy of light into different forms, whether these are charge and molecule. This, as Michelle has mentioned, has been one of our main focus over the years, but also more recently, how can we control the light to heat conversion? And so on the right-hand side of the light path, obviously we have kind of obvious applications in photodetectors, light rechargeable batteries, and photoelectrochemistry. But one of the interesting things one can do is switch the material composition and think of using metals for these applications rather than the traditional semiconductors. And this is really has been one of our focus in understanding how to use these hot carriers, their fundamental properties, their role in photoelectrodes, their role in photoluminescence from gold, and then in upscaling devices, and broadband absorber can exploit them. But then while doing all this work and focusing a lot on metals, which are normally used for heating, we started thinking, what about the other half of this world? So obviously we can also dissipate a lot of energy of light into heat. And what happens now if we again switch the paradigm, and instead of using a metal, we start thinking of using a semiconductor? And obviously there are many applications for photothermal effects. I don't think I have to mention it directly in this webinar. But again, we were interested starting from the thermochemistry, but also how can we use it in kind of active materials, whether they are actuators, but also thinking and going towards a tunable optical component. And so the outline and the motivation here is really to understand what happens when we now have dielectric or semiconducting nanoresonators that do have a thermo-optical effect, and how can we combine these two to realize thermally reconfigurable metasurfaces. And in particular, I will show you the example of a meta lens. And then going towards light-actuated systems, thinking on how do we need to deal with the problem of photothermal effects in collective, in large arrays of nanoresonators, where obviously now we have collective heating effects, and we also have to treat the thermo-optical component and the differential shift in every point. So to start from the beginning, our main characters in this story are the dielectric nanoantennas. We all know them in the photonic community for their optical resonances that can be tuned similar to the plasmonic one. And what is particularly interesting and has attracted a lot of interest is the fact that they can support both electric and magnetic resonance mode that then give more flexibility when designing, for example, the forward versus the backward scattering properties of a metasurface. But what I found particularly interesting about these materials is that we now have two very different frequency ranges of operation. We have an above bandgap frequency range where we can have very, very strong light absorption and therefore charge generation, but also heat dissipation. And we can also have a below bandgap frequency range where now we have very low optical losses. We can have very high quality factor resonators. And so we kind of have two different regimes and two knobs that we can use for designing system, and we can mix and combine different wavelengths of operation. So you see here, for example, using the strong light absorption in the semiconductor, one of the early demonstrations from the group of Mark Brongersma, where they made this ultra small, ultra thin germanium photodetector based on some resonance germanium nanobeams. And again, normally if we only think of the optical application, we want high resonance, high quality factor resonances, but absorption can also be engineered and be quite useful. And so when we start considering a few different semiconductors, we also can realize that a few of them have a significant thermo-optical coefficient. Germanium is the one that has the highest one, but also crystalline silicon and amorphous silicons are not faring too bad. And so we can start asking ourselves whether we can use this thermo-optical effect to locally modulate the refractive index of the material and therefore the resonator. In fact, if we have a thermo-optical effect and we have a resonance mode, as we increase the temperature of this resonator, whether it is optically through a photothermal effect or externally through an external heating of the substrate, we should see some shift, typically a red shift for these materials of the resonance, which is naturally associated with the phase change of the resonator. And so this obviously gives us the building block of a functional and reconfigurable metasurface. So there have been indeed a few attempts in the past in using heating to design metasurfaces and reconfigure them. This was an early demonstration from the group of Schuller, where they realized the lens. One of the drawbacks here, they could show that they could modulate indeed the focal length with temperature, but the operation frequency was also shifting as the lens was being heated up. And this is another sort of hybrid demonstration from a group of Romain Quidin, where they now use rather the thermo-optical coefficient of a PDMS layer combined with a fixed metal lens to obtain a very sizable focal shift of the combined system. And then a little bit around this time, also there was an interesting work where they investigated a little more carefully the photothermal dissipation inside these resonators through Raman thermometry. And indeed, it was observed that they can actually be better than some metallic particles for heat dissipation. And so really, this dielectric nano element can provide us all the ingredients for realizing for an active metasurface. So a few years back, when I started here at DPFL, we started asking ourselves the question whether we could actually search for a way of designing an active and thermally reconfigurable metal lens where the operational frequency was fixed and we could just tune the focal length by changing the temperature of the substrate, and in such a way that all the optical modulation was done at the level of the individual meta atoms that we use to build this metasurface. So this was the work carried on by Dr. Archetti when she joined the group. And indeed, if we want to realize a metal lens to begin with, we have this parabolic phase profile. And then if we want to change the focal length, this means that we basically need to change the curvature of this parabola. So if we want to understand now what does this mean in terms of the requirement that our meta atoms have to satisfy at different temperature, we can look, for example, at a specific radial position along the lens, and we will see that as the temperature increases, this meta atom will have to provide a differential phase, a delta phase, in relation to its temperature. However, we also see that a different meta atom at a different radial position will have to provide, in this case, a larger phase modulation. So if we plot this phase modulation as a function of the radius, we indeed see that a different position along the radius of our lens will have to respond differently to the temperature change. So how to satisfy both of these constraints can be relatively challenging, but eventually we figured out that you can play a trick. So if you use the Pancharatnam-Berry phase to satisfy the room temperature profile, then you can encode only the delta phase into each of the resonators. And by designing still different resonator at different radial positions, you can achieve both conditions simultaneously. So this is the type of resonators we explored. Again, you need a few degrees of freedom to be able to satisfy all of these constraints. We fixed the periodicity at around 350 nanometers. We fixed the height of the resonator at 300 nanometers. Again, we wanted to have something compact and small. And we fixed the gap between the two elements at 60 nanometers to be sure that this was going to be something we could actually fabricate. And then we looked for different elements, these double nanofins, as we call them. So these two coupled pillars where we can change the width and the length. and see how the phase modulation and the delta phase modulation change with the temperature. And as I said, we also use the rotation angle as a free parameter for us, such that we could search and then have different phases in that way as well. So through brute force simulation, I have to admit, now we're trying to do better. We swept this parameter and basically constructed a library of geometrical structures with different geometric length and width at different temperatures and for different rotational angle. And then we looked at every element, every couple of these double pillars, what phase modulation they provided, and then for a given delta t, what phase difference they also provided. And one last constraint that we imposed into the system was that the phase change with the temperature could be fairly linear for the chosen resonators. Indeed, not all of them had a good, reasonably linear change. And so eventually from this wide parameter space, we could identify 6 elements that allow us to cover all these requirements. We couldn't identify a 2π phase modulation, unfortunately, in the delta phase. So we could not realize a lens that was able to wrap up the phase, but at least we could cover the phase range needed for around 50 micrometer diameter lens and around 200 micrometer in focal length. And you see here the 6 elements. In the blue line, this is the room temperature phase requirement. The red line is the high temperature phase requirement, and the dots are the different resonators, 1, 2, 3, 4, 5, 6, that we have to place at different radius position to satisfy these requirements. And here you see the delta phase that needs to be satisfied again by the resonator 1, 2, 3, 4, 5, 6, and you can see which one needs to be positioned where along the radius of the meta lens. So this is how the point spread function of the metal, the calculated point spread function of the metal lens looks like. This is the focal point. This is along the propagation length. Obviously, this is a relatively low NA lens. We also applied it to a higher NA lens. And we indeed, if we account for the response at the different temperatures, then we can see that the focal length can be modulated from around 165 to around 135 by changing between a room temperature and 220 degrees. And we chose this temperature range because it was something that we could eventually test in the lab. Obviously, the larger the temperature change, the higher the modulation. And the full width of maximum is good, and also importantly, this is a circularly polarized lens that operates under circularly polarized light. One important thing is the conversion efficiency. Obviously, the maximum is 50%. We also use this constraint and only use meta atoms that had at least a few tens of % of efficiency. So the average conversion efficiency is around 26%. We also try to fabricate the structure. So here you see one scanning electrochemical microscope image of the system, and where you can probably now understand better the ingredients of this design. You can see in this image 1, 2, and 3 different pairs of meta atoms. You can see the rotation along the radius, but you also see that at some point the meta atom switches its design. So these 4 are the same meta atom that gets just rotated to satisfy the Pancharatnam-Berry phase, but then at some point we also switch the design such that then during the thermal modulation this continues to satisfy the phase change. And we tested this with an external heater. These are the simulation for the propagation, for the point spread function along the propagation length from 20 degrees to 230. And this is the cut along the center. And these are the experimentally measured profiles. And we can see a reasonable agreement. There were also some disagreement. And unfortunately, after the fabrication, we realized that the crystalline silicon we purchased was grown on a sapphire, which we knew, but we didn't realize immediately that the sapphire is not a C-cut, it's not a C-plane, but it's actually an R-cut, which then is birefringent, and therefore there might be an influence of the change in the incident polarization when we increase the temperature due to the light that propagates through the sapphire. So we wanted to repeat these experiments, but also we decided that we are more interested in going towards light-driven photothermal modulation rather than external modulation. And so before we make a new design, we wanted to step back and start thinking more, how can we eventually use light to really drive and modulate the system? And so this brought us to think more at the level of the single nanoresonator and at the level of the nanoresonator array. How can we model and understand this photothermal and thermo-optical coupling combined? So obviously, if we use external heating, how we did or we thought in this first proof of concept design, what we do is that we consider a certain heat flux input to our system, which will determine a certain temperature profile, and then this will correspond to a certain absorption cross-section of our individual meta atoms. And this is fairly deterministic, and as long as we have the freedom to control the heat flux, we will control the temperature, and this is fairly straightforward to do. If we now start using an optical self-heating or due to photothermal dissipation, however, this becomes clearly an interactive loop. So we absorb a certain amount of photons, we generate a certain amount of heat and reach a certain temperature. This determines the absorption cross-section, but this cross-section will be different from the initial one, and so the system will eventually have to settle on a steady state temperature that will depend on the intensity and the initial absorption cross-section. So if we look here, this is the absorption efficiency for a silicon nanosphere. I think this is 33 nanometer radius, so 66 nanometer diameter. And the blue one is the room temperature spectrum, not too exciting. There's primarily the electric dipole, but then we see that as we increase the temperature, the spectrum shifts, red shift in this case, and also broadens out. So for example, if we now imagine operating at the wavelength of the initial room temperature peak, if we plot this absorption cross-section or absorption efficiency as a function of temperature, this will be decreasing significantly. On the other hand, if we start at a more red-shifted frequency compared to the initial resonance mode, we will have a significant increase of the absorption cross-section with temperature. So basically, if we now look at this in terms of the temperature change as a function of the intensity of the irradiation, if we start by illuminating on resonance at room temperature, as we increase the intensity, the resonance mode redshift, our absorption cross-section will decrease. Therefore, our temperature increase will be sublinear and will tend to a self-limiting value. On the other hand, if we start off resonance, so again, our green curve is the room temperature, we start initially off resonance, we're not that efficient at the beginning, but as we increase more and more the intensity, we will go on resonance, and therefore we will have a phase where our temperature increase is highly, very steep, and what we can say sort of divergent, until the point we reach the peak, and then we will fall back into the self-limiting mode. So we can now look, what does this mean for some more interesting optical modes? So for example, here we looked at some silicon nanodiscs that have this anapole mode, which has a dip in the scattering and the peak in the absorption cross-section. And we computed how the resonance would shift as a function of the intensity of the laser. And what you see here is that if we increase the intensity of irradiation, the shift in the resonance mode, it's totally nonlinear, and we will have an initial slower shift and then a faster shift with intensity due to this nonlinear change of the refractive index with temperature. And we also did this for germanium nanodisk, where things even get a little bit more complicated, and there can be even a non-monotonic change with an initial bump, a decrease, and then an additional increase due to this interplay between the two effects. So this understanding of the photothermal and thermo-optical effects at the level of the single nanoresonator can be explored further, and actually has been the focus of a few works in the literature. For example, looking at how these strong nonlinearities in the scattering from a single silicon nanostructures can be exploited, including for some super resolution, as well as how some bistable resonators can be designed to have very, very fast switches in terms of temperature and scattering spectrum as a function of the incident wavelength. So certainly this in itself is something that it's still worth interesting and can give more knobs for applying these thermo-optical effects in individual elements. But as I mentioned from the beginning, we were also interested in thinking about the metasurface design and concept. And here, definitely we are not thinking of single elements, but we have very large array with thousands of different elements. So how can we treat these two things together? And the problem is that, as we know well from thermoplasmonics, as long as we are in a single nanoresonator, things are, again, fairly straightforward. We absorb light, we generate temperature, and in this case, we would just iterate back on the absorption cross-section. But now, if we have an array, when we absorb in a given resonator, we change the temperature of that resonator, but because of the collective heating, we will contribute to the temperature change of all of the other resonators. And so this sum of these two terms will then affect the initial resonator. So there is a very complex spatial coupling in addition to thermo-optical coupling between the different elements. So to understand this, again, we use a framework similar to the one from the thermoplasmonics, where we can decouple the temperature into the two contribution, the self-heating contribution and the collective heating contribution, only that now in the absorption cross-section that enters into the self-heating contribution is a temperature-dependent term, and it will be related to the temperature at that specific element in the array. We also use a framework. Again, this is the first attempt, so we just use spheres, such as you can use me theory to get these absorption cross sections, and we operate in an uncoupled, electromagnetically uncoupled situation, so that we don't have to simulate or calculate the coupling between the different ones as they heat up. So how does this look? Well, let me show you what happens with a relatively small array. This is a 5 by 5 by 5 array of silicon sphere in a regular grid. And these are the two calculated self-heating contribution and collective heating contribution, assuming an incident light coming from the top and propagating through this array in the absence of thermo-optical effects. Now, because in this system, we basically pretty much have to worry only about the light absorption in each element. As we can see, the self-heating term of the temperature follows exactly the intensity of the illumination profile, while the collective heating effect follows the sort of the largest number of nearest neighbor, or the fact that the central one is the one which will have the maximum contribution of diffusive heating from all the other elements in the substrate in the system, while the corner ones obviously will have less contribution of the diffusive heating. When we switch on the thermo-optical effect now, and we start computing the solution with a temperature-dependent absorption cross-section, then we see that the collective part is not too much affected, but the self-heating part is. And in particular, we see that there is no longer a uniform temperature across each plane in the grid, but indeed we start imprinting back the collective heating pattern onto the self-heating pattern. So there is really this crosstalk between these two effects. Something interesting also that one can try to look and compute is ask the question, let's assume that I have the same number of photothermal particles. I just arrange them differently in a one-dimensional series, in a two-dimensional plane, or in a three-dimensional cube. And then I start illuminating them, and I increase the number of particles, so I increase the amount of collective heating contribution basically in the system. And what one can see is that obviously in the 1D, the collective heating is less efficient because the particles go further and further from each other. But in the 2D and 3D, again, we can have that the average temperature of the system rises very rapidly with a number of particles. And now, if we consider two different illumination wavelengths, one on resonance and one initially on the right of the resonance, there is going to be a certain number of particles after which it's convenient to switch wavelengths to continue heating the system more rapidly. So these kind of thermo-optical interactions can lead to all kind of different behaviors into this system. What is also interesting is to consider...
Excuse me, Giulia,
yes.
5 minutes left.
Perfect. Thank you, Michelle.
Thanks.
So if we now consider what happens if we now have a relatively small, like 5 by 5 sort of grid, but very extended, so hundreds of elements or in this grid, obviously we will have that the light, as it penetrates into the system, decreases its intensity, so we will have the decay in the temperature profile along the system. The baseline is the self-heating, it's the collective heat in the part, and basically the peaks that you see are the self-heating term on top of it. What you see here is that as we make it very long, the temperature peaks rather close to the front surface because of this collective heating term. Now, if we switch on the thermo-optical effect, and we initially illuminate on resonance at the room temperature resonance, the overall temperature profile will be affected because the self-heating contribution will decrease in the front of the array, and it will increase at the back of the array, and so will do the collective heating. And so we have this sort of temperature redistribution along our array. If we have only a 2D system, things are a bit less exciting to begin with. So in light blue, we have the case without thermo-optical effects. Again, we are just illuminating 51 by 51 of these silicon nanoparticles. They have our temperature profile, which peaks at the center. And if we introduce the thermo-optical coefficient and we start redshifted, they will go on resonance as we heat up, and the temperature we will reach will be higher and with more curvature. But now we can also start asking ourselves, okay, I just use a simple system where all the resonators were the same. What happens if I can now play with these resonators and have them initially different? So if we look what's happening here, now we can look at the change in the absorption efficiency between 250 and 20 degrees Celsius for two different silicon spheres, the 33 nanometer sphere and the 53 radius nanometer sphere. So if we look at the smaller sphere, it will have a dip in its absorption efficiency at the initial electric dipole mode. But then this means that the mode will redshift, and at around 410, we will have a peak. But the larger sphere obviously starts shifted, so it will actually have a dip at 410 and will have the peak redshifted. So if we now design a system that operates at 410, as we increase the temperature, we will have that some of the resonators will go on resonance and some of the resonators will go off resonance. And so we can start playing with their self-heating and therefore also with the collective heating. And in particular, if we make it such that the external elements that are those that in the uniform grid were the colder ones, we can partially compensate the effect of the poorer collective heating at the edges of the array by making them more effective in absorbing light. So if we now consider this array with the smaller sphere in the middle and the larger sphere at the center, you can see the calculated temperature profile if we have no thermo-optical coefficient, and then if we have the thermo-optical coefficient in red. And you can see that with the thermo-optical coefficient, as the system heats up, it tends to kind of equilibrate itself, with the edges going a little bit hotter and the middle one being a little bit colder than they would like to be originally. And if you look at it, this kind of smoothen out the temperature profile in the system. One can use a different wavelength and do a similar trick. So again, this is the initial temperature profile will be very non-uniform. And again, when we heat it up, we can kind of flatten it out. So it's kind of interesting because if we think now we can try to design a system where we have a uniform light-driven temperature profile even across an array of systems. Obviously, this would then be an additional constraint that we have to bring in the design of the metasurface per se. So this is where we are at this point. I think I hope I showed you that thermo-optical effects in these resonators can be an interesting tool to modulate the response of these optical elements, and that by controlling it even in an array, one can actually obtain some interesting designer temperature profile that could be used to actuate metasurfaces. Obviously, there are still a lot of questions. I think one of them is what happens when we have optical coupling between these elements. How can we explore coupling or decoupling of these elements? And what would happen if we were to use collective modes in the array, something like more lattice mode in our system? One big questions are the time dynamics, for sure. What I think it's interesting is that still each of these elements is very small. So at the level of the individual elements, the heating, overall the heating is going to be very fast. The cooling will be slower, but it will be interesting to explore how fast one can cool this system, and then eventually try to understand, use silicon or amorphous silicon because they're the most easily to treat and to have available in the lab, but what other material could be interesting for this kind of application, and try to really put all these pieces of the puzzle together to understand how we can use these components for thermo-optical modulation. So with this, I would like to thank the team. In particular, the work I presented comes from Anna Archetti, Ted Sulos, and Alfredo Neff, and recently Dr. Mohammadi. But I would also like to thank the funding and obviously all of you for your attention. Thank you.
Thank you very much, Dr. Tagliabue. And I think it's open, the talk is open for discussion. I don't see questions in the chat, but you can raise your hand. Maybe you can start while people prepare questions. You mentioned that metal particles were actually less efficient for heating than semiconducting particles, which is a little bit counterintuitive to me. So how can I understand that? I mean,
well, I think it really depends on the wavelengths and the strength of the mode. But the fact that by combining the electric and the magnetic mode in these dielectric resonators, you can create very, very, very strongly absorbing resonance mode, more than you can do with just a pure electric mode in a plasmonic nanostructure, basically.
So this is a consequence of the absorption of light, not so much of the conduction or transmission.
No. I would say
because, for example, in radiative exchange, this is well known that metals are, being reflective are less conductive. Yeah. I mean, they tend to isolate better, right?
Yes.
Than semiconductors that can radiate. So in radiative transfer, this is well known. But in this case, it's just the amount of energy.
Exactly. Yes.
The power
it's about the amount of energy.
Okay. Now
yes.
I understand. Thank you. Are there more questions? I cannot see all of you at the same time, so I have to switch between the two different.
I think Frank has a hand raised.
So just speak up.
Yeah, thank you very much for the nice talk. Because you mentioned at the end the dynamics, so you said it's slow, the heating up. No, the cooling is slow and the heating is fast. So what is fast and slow on your?
Yeah. So the heating fast, it can be very fast. It's the order of sub-nanoseconds for sure. The cooling will depend on the dimensions of the arrays, because that will really depend on how well and how fast can you carry away the heat. So I think currently we've tried to do some measurements. Definitely we see the microseconds level, but I don't have a bottom number on what you can do right now, which is what we want to explore. And I think the conductivity of the substrate and the surrounding will play obviously a big role, and the size of the array that you're using will also play a role.
Okay, so where do the nanoseconds come from? They are just the temperature of the individual elements, but not in a stationary state with the environment, right?
Yes.
Okay.
Exactly, but if you imagine that you want to modulate, right, you could modulate during the ramping up and the cooling down of the temperature, right? So you could exploit the transients for the modulation itself, yes. but the rising temperature will be faster than the cooling of the temperature.
Okay, thanks.
Any more questions?
I had a follow-up question.
Please, go ahead, Helga.
So I'm envisioning the ramp up in temperature and reach a steady state. It is now that steady state probably is pretty dependent on the overall intensity as well. Mm-hmm. How do you let's see? How should I be interpreting where the steady state lands and what's happening as it gets there? If that makes sense. I mean, is this all going to be optimally configured for the steady state response, or are there advantages to considering the time dependence associated with that temperature change as well?
Yeah, so I think really the interesting part is if we can exploit the time dependent of the temperature, because again, that's where we can exploit going fast, at least heating fast, and maybe try to make also the cooling part sufficiently fast such that the repetition rate maybe can be adequate for the application. So I think definitely that needs to be designed. I can maybe give you a number. We did a test for just a simple Metasurface consisting of only amorphous silicon disk this time, because we switched away from the crystalline silicon, so we don't have the sapphire issue. And we have used 10 milliwatts focused in a beam of around 5 micrometers in diameter. And we could, did I say 10 milliwatts in 5 micrometers? Yeah. Yes. And actually, based on the Raman spectroscopy, we could see almost 400 degrees increase in the temperature of the disk. That was sufficient to get a 50% modulation of the transmission of the surface. So again, we couldn't do yet proper time dynamics, but that's what we want to explore next and try to understand that better. The thing is that, again, there is a challenge in simulating the real elements which are coupled with all the time transients and all the elements. So that's why we try to start with some simpler model that could give us some indications.
If you immersed in a liquid, would that facilitate that rise to steady state, or could you control the heat dissipation by?
I think it would facilitate the cooling, right? You want something that can cool better, right? For having a faster cooling. So yeah, anything that can have high thermal conductivity for the cooling would be beneficial. Obviously, then the peak temperature is going to be affected. So one has to find the trade-off between the two.
Great, thank you.
Thank you.
All right, we have a question from Julian Gargiulo. I read it. Thanks for the amazing talk. What do you use for temperature measurements?
Yeah, thank you, Julian, for the question. We do use, so for the lens test, we just use an external heater. So we first calibrated it as a function of a current that we passed and the temperature that we reached. And we did so also for now ellipsometry measurements. In these cases, we use Raman spectroscopy. So we use the Raman peaks of the silicon or the amorphous silicon. And again, we calibrate it with the external heater first. And then we can use it to measure during the experiments.